Hey everybody, how are we doing? It is Wednesday. It's the middle of the week. I got some coffee. Got the veterinary medicine mug today. Good coffee. Get some power up. Who is here? Who is here? We'll talk about some decision trees to start. We got some really cool data. Let's take a look at it. Hair's just going everywhere. Just keeps getting longer. Let's do this. Hey, Kayla, what's up? I sent you a code and some questions on Discord. Awesome. Let's check that out. Kayla, I'm going to show this also today in class. Here, I'll show this really quick. We had Stat 1 students report their scores and some variables. Good to see you. Thank you so much. Here, we'll go take a look at the code right here. Look at this. So this is a decision tree to predict why people are successful in the class or on the exam. And the number one thing was Canvas content, which has questions. So for 2-1 students, if you're seeing this is a lot of my students answered questions. So take a look at this. We're going to hop right over to the question in 2 seconds, Kayla. And then I want to put this in the video so they can see. And then my Pearson grades come into play. One thing I did notice too, though, and do 10 decile reviews, which actually has an interesting relationship. But one thing I noticed here, which I want to point out to, I'm going to run all the variables on this. These are all the individual plots. We're going to go right here, and I want to show some analysis on this. So these are people who watch the Kahoots, and you can see right here the people who are watching the Kahoots, their grades are a good bit different. Now, it's only 2% of the variation, but there's a tighter distribution for the people who watch the Kahoots than the people who never watch. I mean, someone got 100 who never watched the Kahoots. Awesome job right there. Or they got a 98. That's the 100. 99, the 100. Oh, it might be someone who watches recorded Kahoots. So the person who got 100 watches the recorded Kahoots. But there's a tighter distribution right here. That's a tighter distribution. This is the Canvas content, which explains 12.5% of the variation by itself, which is insanely statistically significant. This one was actually not statistically significant. So the biggest thing we see is Canvas content. Like, that is big. We saw also, we redid our data, but what was your score? Do you watch office hours? So we see right here, but it's not a random sample, but still, that's interesting. It's so interesting. Where's this? What do 10 decile reviews? Oh, there's always, so very little data there. Let's look for statistically significant. This one is, do you take notes while watching class? Kayla is a big one right here that I saw. This is statistically significant and accounts for 5% of the variation. Do you take notes while watching class? You can see right here the distribution of people who always take notes, sometimes takes notes, and never take notes. And we can see the confidence intervals for the means of those groups. And you can see the always taking notes had a confidence interval for a true mean of between about 85 to 89, where never taking notes has a confidence interval between 77 to 84. More variation in the never taking notes, probably a smaller sample size. Yeah, 27 people. So the people who report that they're always taking notes have a higher, and it is statistically significant. This variation is unlikely due to random chance between these means. So that's what we're always talking about with p-values here, is the differences we see between these groups are unlikely by random chance. And so it looks to be there is something to always taking notes in class. So it doesn't mean you will ace the test, and you could never take notes and do well on the test. But if you look at the grades right here, I think there's our 100 again. Did we see anything else that's statistically significant? This one is, but just barely. This one is the question, nope. How attentive are you in class? And the highest group is very attentive. So we can look at the means of the groups down here. Very attentive had a mean between 85 and 91. Where very distracted had a mean between 67 and 86. Smaller sample size, more variation, more uncertainty. I know writing helps you remember. That's the biggest thing. That's why I'm always like asking so many questions. I'm always like, what do you think of this? And I'm like, come on, everybody. Like, please keep answering. Please keep answering. I'm so glad, Kayla. I know you answer a lot of questions. I want everybody to answer as many questions. And you know, I encourage more people to answer. I'm like, come on, we need more answers, even if it's right. I'm like, just copy the answer. Just get it down. Write it down. If you're typing in the chat. Here we see my Pearson grades. This is a very small sample size and thus more uncertainty. That's actually the confidence interval right there. Jump shows you the confidence intervals basically with these diamonds. There's a whole bunch of uncertainty with only 3 people answering that. But we do see the difference between the A and the B is drastic and super statistically significant. Last but not least right here, let's go over here. We have a regression. This person said they studied. I'm going to hide and exclude that person because they're an extreme outlier. So does studying help for the test? It's looking like no. Let's go look at that plot, and then we're gonna head over to the 320. Yeah, that's not statistically. That almost looks like the what. So Kayla, great review question. Thank you, Kirsten. I find it so interesting too, and we can draw insights from this to think about, like what helps. Well, first off, I know I'm not just trying to be like, hey, come to class and take notes, but those have been the two most important variables. Yep, looks just like the naive model. Yep. And the p-value is super high, looks like a flat line. The slope is super small. There's the slope. It's actually negative, but probably just due to random chance. MuBot, they don't have to tag me. Or they can check, yeah, you're right, MuBot. Oh, wait. MuBot, you're on? Oh, good. Glad you're here, MuBot. I forgot to click the button, but you're here anyways. Do you watch speedruns? Ooh, all of them. And it is statistically significant and explains 5% of the variation. But we see right here, but these two groups have a little bit of an overlap. You can do this thing called a connecting letter reports. You can do all this in R too, but sometimes it's quicker doing jump, but you can do high level things in R. Like, Ryan, why are you not using R? Showing it to a 1. I think we want to go for the all pairs Tukey's. And so that should be the follow-up test down here. Is it going to give me a connecting letters report? Yeah, so the big difference right here is between the all of them and the sum of them. So you can see the connecting letters report. So there's difference between the all of them and some of them. And this is a family-wise alpha test. A lot to talk about there with family-wise alpha and stuff. Last but not least, we do not see statistical significance of when did you start studying for the test. That's interesting. It wasn't when you start studying. You know what? Hey, what's up, Michael? So good to see you here. You know what I find so interesting about this, it's not really when you started studying for the test that made the difference. It's more what you were doing in class. Like, here's when people started studying, not statistically significant. Like, that's super not significant. What really mattered when we looked at the statistically significant things was this is statistically significant. Did you do your visualizations? So doing the visualizations helped. What else? What are your My Pearson grades? So doing the My Pearson work, that helped. But the most statistically significant things we saw, this one was really statistically significant, was do you take notes while watching class? That was really statistically significant. And last but not least, we also saw over here, was that statistically significant? Oh, this is statistically significant. I think this is because of self-sampling. The people who never go to SI reviews had higher, but there's only one sample here. Look at that confidence interval. It's ridiculous. It's not random. SI reviews, huge help. Alyssa, thank you so much. And we also see right here the Kahoots and Canvas content. Canvas content was maybe the most with 12.5% of the variation. So probably if I can give the biggest advice, it'd be do your Canvas content. So 201, real quick advice right here, looking at this data that we have, preliminary data. I'm going to keep collecting more data and analyzing it. Number one thing, do those Canvas content. Know the Canvas content, do the Canvas content, do the Canvas content. Number two, check out the Kahoots. That accounted for only 2% of the variation, but it is statistic. Oh, that one's not statistically significant. Don't listen to me. Be attentive during class. We see the attentive had the highest, statistically significant. Next, we see do your My Pearson. That had a very, 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 very statistically significant and accounted for also 12% of the variation. It's really the difference between the A and the B we're looking at right here. So get A's on that. And also we saw be attentive. I'm just going by the data, everyone. Just letting the data guide what we're talking about here. We'll have more data, but let's hop over. I'm going to pull up Kayla. Good questions. Let's take a look. Okay, here we go. 2 seconds. I'm going to go to space. I'm going to pull up your file, Kayla. Kate is pulling up. And changing ID to 5555555555555. I'm going to go to the parts you're interested in because I want to show the whole thing. Okay, wait. Oh, you got your questions right here. That's so good. Linearity assumption. Further explain why we want... Oh, okay, yeah. Let's talk about this. This is really good. Let's talk about that part right there. And I'm going to try to do it by not doing it. Oh, this looks great, Kayla. Amazing work. Let's talk about these assumptions right here. I've got your file, and I'm going to go down here. Make sure this isn't 2 seconds. We're going to do it. This is another. I think I have a blank copy of it somewhere. I have so many copies of this file. Okay, let me see. Okay. I think we got it now. I think we're good. Okay. You're welcome, Kayla. Thank you, Kayla. I'm just getting everything ready. Let's go over and let's check it out. I'm going to make sure I try to cover all the questions right here. And so good to see everyone here. Michael, Kayla, Kirsten, everybody. So good to see you. Let's talk about these assumptions right here. I'm going to pick some fuzz off the microphone. 0, there we go. So let's talk about these assumptions and what they mean. So whenever we make regressions, like, do I have a regression stored right now? Let's see if I have one stored. I do have a regression stored. I have the classic height weight regression that we do all the time right here. So you need to first make sure you have a regression created. So to create a regression, we usually store into, any idea why we call it M? Kayla, do you have any idea why I usually just call it M? Like, why would Brian call it M? You can call it whatever you want. You can call it any name you want, but I usually just call it M. And M stands for something, but that's why I call it M, like, because it's a this. So it's already on the right it's like behind me right now. But I'm just making a classic regression right here. The one we make a lot of times in class. Because if you know how to understand one really well, you can just take that understanding and move it over to another one. Model, exactly. So you might call it like model 1. You could literally call it model, like whatever you want to call it here is whatever you want to call it. And then it just has that name as an object. And you will see that object appear in the brain of R. So when I make this right here, that will then appear in the brain of R. See, I already have a model here and a model here. It's actually a list. To get into some technical aspects of this, there's actually a list with a bunch of things contained. So you can actually go inside of the model with a $sign and take a look. And there's even like lists inside of the list inside of here. So you got lists inside a list inside a list. It's pretty insane. It's pretty cool. So that one doesn't have more lists, but it's a list with more lists, with more lists, with more lists. Yeah, QR, I guess, has more. Yeah, so you can do that, and there we go. I don't even know what that is. Maybe I should. What is QR? I don't know. You don't need to know what that is, but you can get other things out of here. You don't have to, but you can get the residuals. So that's a really good way to get your residuals if you want. You can get the effects, which are going to be, I can't think what the effects are. The coefficients of them all. There's the coefficients. But rather than doing all that, we get pretty much all we want right here. The summary is a function that changes based on what you put inside of it. So with the summary right here, we can actually just get the main things we're looking for. Now, we don't have to do a summary on this one. What we're actually going to do is do a function Dr. Petrie created called check regression. And one thing I want to point out right here is the check regression is inside a reg class. I know it's inside a reg class because it says reg class there. If you're running check regression and if you type check regression and you don't see it, that means you have not started library reg class. So make sure you have library reg class going. That will give you access to the function check regression. Now, Kayla, I want to show you some cool stuff right here, is that if you go over here, you can actually go to the reg class package and you can actually see the functions inside of it. So you can actually see check regression is right here, and you can do this by changing which thing you're looking at. So if you're ever wanting to think like what other functions are inside of this package, you can look at the packages you have on. You see I have a bunch of other ones like random forest, string R, I get a little ggplot or different things, and I could then take a look at these functions that are inside of here. I'm going to go back to the global environment, which is the main brain of R. Like that's the main thing R knows. These are kind of the other things it knows in the background right now. Like I have this attached. Oh, I never noticed that until I started attaching things. So these are attached currently to the main brain of R. That's why I can access them without typing the full data frame $sign. Okay, we got the check regression. Yeah, I like dropping these little hints. Like I want to always like teach like at this level. Then someone will be like, here's like the cooler things. Here's like the extra things that it's always good. So what we have right here is some issues. So sometimes people get super excited because they're like, yeah, low p-values. All low p-values mean is what? All the low p-value means is you do what when you see it? Like all the low p-value means is you just do this. Like when you see a low p-value, you just say, oh, I'm doing this today. Same thing we do every day, Brian. What do we do when we see a low p-value? When the p-value is low, da-da-da-da. When the p-value is high, just let it fly. When the p-value is low, da-da-da-no. What am I saying? When the p-value is low, when the p-value is high, just let it fly. It is statistically significant, exactly, and we reject the null. So and it always means exactly. When the p-value is low, reject the null. When the p-value is high, just let it fly. What do I mean by let it fly? Well, I had to make it rhyme somehow. When the p-value is low, reject the null. When the p-value is high, just let it fly. It just means just let it be. Nice job, Kirsten. Let's throw some 50 points out. We haven't given out points today, so let's do it. Thank you so much. It's practice. You just have to know when the p-value is below 0.05, you have to reject the null, and that means statistically significant. It means our results are unlikely by... You knew it had to happen once today. It means our results more extreme or unlikely by random chance, but we usually just try to like, if I'm going to communicate this to somebody, here's how I'd communicate this to a non-regression person. Like you'd say, well, Brian, why do we have to write so much? Well, because I have that knowledge in my brain. I'm going to sum up all of this right here very quickly. You ready? Here's my communication to somebody who doesn't know statistics. This model I've created has some pretty big problems. I don't know if we should be using it because things like the linearity might be a problem. Like we put a line to it, and that might be a bad idea. Also, there's some extreme outliers that are probably not like well predicted, and they're also bending the model away from it. I'll highlight what I'm talking about. I'm talking about this one. And also, probably last, but not that big of a concern, is there's some issues that the model has a change in strength as it goes out. So, I mean, when we talk about the R squared and other values, like when we try to talk about how well this model helps us understand, I don't know if it's consistent throughout. So we're not really going to see consistent results with this model. I'd have hesitations on using this model. We could probably make a better model. So let's go back to the drawing boards on this one. Hopefully that didn't sound too statistically. I kept dialing myself back. As soon as I said R squared, I was like, oh gosh. Oh no, I shouldn't talk about, oh no. I shouldn't talk about R squared. I shouldn't do that. They're going to be like, what the heck's R squared, Brian? I'll be like, yeah, don't worry about it. It's just how well our model does explain the points. And the consistency in that is pretty bad. R squared is a derivative of R. And if we have a change in strength, like if the model changes in strength, we're going to see a change in the predictive power of the model because correlation leads to R squared. So the change in predictive power in this model, where it's getting a little bit tighter towards the end, which is shown up by the equal spread problem. Yeah, this is like, I don't love this model. I don't like. So you might be wondering, wait, I thought low p-values are good. Well, we said at the start, anytime we see a low p-value, it just means we have statistical significance and we reject the null. So it's really interesting because this connects to 201. There's Niagara Falls again. We took a class field trip there yesterday and Monday. it's our one class field trip. So we do not use stat vocabulary like, no, you can use it. You always want to like, the more stat vocabulary you use, the more you want to explain it without stat words. Like that's why we talk about, like R squared being like how close we are, or how much we understand in the Y variable due to the X variable. Like using the X variable gets us this much of the way to understanding Y completely, or the variation. That's why we could talk about the sum. Like the worst thing to do, and this is what we would not do, is we could say something like our model decreases, which I will accept probably. I just don't want us doing that, especially on the test. It's like, well, you are right, but we do try to say things in like a something people would understand outside of our world. A too complex way to explain R squared would be the reduction of the sums of squares from calculated by the naive model. Our model has reduced the sums of squares from the naive model by 40% of the total that exists. This reduction was found to be statistically significant, which is unlikely by random, which means it's unlikely by. We have to be careful. We have to say, my model that was created to explain height using weight. What's the R squared on it? My model that was created to explain height using weight accounts for 40% of the variation in height, or 36.1. So listen to the two answers right here. Just brief talk on this. We can just go classic right here. 36.13% of the variation in height is explained by the variation in weight. That's just classic. That's how I do it in 201. We do it that way here too. There's other ways that are in the notes, like, it gets us this close to understanding, perfectly fine. This, I think most people would understand this. Like, this is how much of the variation in weight we understand. I mean, height we understand. You could also, but here's what you don't want to do. Like, this is good interp, and let's go bad. A bad one, or too statistically, this is going to be true, but it's going to be too statistically. We could say the sums of squares. Let's go really bad right here. I mean, let's go really too much. ANOVA model 1. And there's that. Which you're like, Brian, didn't you just have us calculate this? Yes, we need to know the mathematics. The sums of squared error from the naive model was calculated. I don't know how to do that umlaut. Whoops, sure. Was calculated to be this with our simple linear model. We have created a reduction in this. I mean, this is how I teach it and how the level we should understand it at. You're like, well, it's just, it's like, well, if we just don't want people to memorize stuff. Does that make sense? We don't, it's tough because in 201 we go for more for memorization, and 320 we go for more for like a deeper knowledge of why. So hopefully you can understand and explain to people and talk about the importance of it. And then when we get to the higher level algorithms, they also make sense. Like decision trees actually use sums of squared error and reduction in the sums of squared error. That's actually what a decision tree does. So I kind of like mentioned that to him for like a half second. I was like, oh, I should not talk about sums of squared error here, but it actually searches through all the variables, Kayla, and it finds which variable has the greatest reduction in the sums of squared error, and it does it at all unique points in each variable for quantitative y. Categorical y's are different, but understanding the algorithm and how it works can help us then choose algorithms. And so that's kind of important when you understand your statistical tools and what they're doing. So we have to have this background knowledge more than just like memorizing a sentence. And in tool 1, we just maybe go more for like a quick overview of topics. And then in 320, like we still want you to be able to explain things at like a lower level. And I do mean that, like you can't go high level on everyone. So this right here would be too much. Yeah. And so hopefully that makes sense right there. Let's take a look at the null hypothesis. So the null hypothesis for any conditions that we're checking right here is that the condition is good and the alternative is bad. I think they made it this way because they want you to use the model. So the null hypothesis for this is that any condition is good until we have evidence it's bad. Does that make sense, Kayla? Like you're going to assume any condition we're checking right here is good. Like any condition we check is good. So we're going to be like, any condition is good until we have evidence it's bad. And so using the general person, yeah, exactly. Yeah, it's like use the skeletons and then work with it a little bit. And so when you look at this and we look at our results right here, look at all these p-values right here. And then let's just talk about it like just like general interpretation. This is checking the linearity of the model. I think it's a little more obvious if you look at this right here. Do you see where the linearity of the model is getting pretty bad? Do you see anywhere the linearity of the model is a little bit lacking? Like where maybe the linearity of the model, because I'm going to change it. Do you see anywhere where the linearity of the model, do you see anywhere where the linearity of the model is getting a little bit like, I don't know if the line's going through the middle of the points. Like you want this line to slice through the data. Like the goal of the linearity of the model. The goal of the linearity, like if it is good, here we'll draw a good and bad for each of these. If it is good, then the line will like slice through the data. The line should like slice through the middle of it. That's good linearity. Bad linearity, we'll do in red right here. So when we have bad linearity, it's going to look something like this, where it's slicing through and then it's not slicing through the center of the data anymore. And so you usually have to have some sort of balancing on that. So yeah, exactly, at higher. And that's what I'm showing right here. It's like it needs to cut through the middle of the data like that top one does, but the bottom one does not cut through the middle of the data. And there's infinite ways it can go wrong, but the line needs to be kind of at the center. Like let's do this one right here, a third one. And would this model right here be good or bad for linearity? Would this model be good or bad for linearity? And just remember how we know if it's good linearity or bad linearity. Would that model right there be good or bad linearity? So look at that new blue model right there. And just think about, would that model right there be good on, be careful. It's good linearity, but it has another problem. So that one's good linearity. And the way to tell if it's good linearity is if you think about how the line's slicing through it, if the line kind of slices through and makes like cuts through the middle of it. So if the line's cutting through the middle of the data, so we should see like an even split on either side. Like the line's cutting through the middle of it. Imagine like that's a slice of pizza and I cut the pizza in half, so the line's going through the middle of the pizza. So that one actually is a different problem, which I'll cover next. So this is the linearity check. And so we have concluded with our model right here that it's good with linearity or there's a problem. You can also view it visually. So, yep, that's the problem. Yep, that's going to be the problem for that one. And so let me kind of also mention here, if you fail this right here, which we did, these two p-values for the simple linear will be the same. Here's the process, and we'll talk about this in the next class, like today or tomorrow for 320. Step number 1, check your p-value. So let's write this down for everyone to see. Step 1, check p-value. If above 0.05, is that good or bad? if 0.05 or above, technically. And let's make this clear, because this only works for checking assumptions for regression, or any assumptions usually for any model. Checking assumptions for statistics. I don't think I've seen any statistics things not go by this methodology. Well, ours is going to have some unique things after this. Like this part applies to all. So this first thing applies. And then the next steps. So is this good or bad? What will we do right here? So we're going to check the p-value. And if it's above, exactly. So this will be good. So this is good. And this is going to be bad. I'll do some color right here. So if it's below 0.05, we actually fail and we have evidence of an issue. So the good is when it's 0.05 or above. That's why when I looked at this, I said, oof, that's bad, that's bad. So now step 2, don't want that anymore. Step 2, sure. Step 2, see if sample size is 25 or greater. Yes, continue. No, stop. Game over. Don't use. Okay. So you can continue on if you have at least 25. This is going to be like, this is not like a pass thing. It's like a, I mean, I'm trying to think, like, would I call it a pass? I'd say like, it's like, we get to continue checking to see if there's good or bad through this. Step 3, and I'm going to do the process on this. Step 3, look at plots. Plots, visually good. Yeah, that's what I thought. Visually good. Visually bad. I just spelled it wrong twice. So good. We'll talk about how it's visually good or visually bad. And well, I've already drawn the 1. Okay. So this is the full process right here that you need to make sure people understand while you're doing your assignment. This is key. This is how to get all the points. So does that make sense, Kayla? This is how for the second part to get all the points. I really want the graders to not be like mean on this, but if you just say it's good, it's good, it's good, like here's how to lose the points. How to lose the points on the second part is to say like, my model's bad, I won't use it. Well, I mean, yeah, it's kind of true, but I don't know. You got like a 50-50 shot if you say it's good or bad, but why? The why is super important. The answer yes or no can often be debated in statistics. I bet someone would debate to use this. I could probably find a statistician out there be like, yeah, I'd use that. I mean, all models are wrong. That one looks pretty useful. I'd be like, yeah, it is kind of useful, but there's problems. I'd be like, yeah, all models have problems. You're going to fail some assumptions. I'd be like, but we fail all of them. They're like, yeah, whatever. So you have to debate it. You have to explain. Does that make sense, Kayla? You can't just say like this model's good or bad and then get all the points for these questions. You need to go through the conditions like and make clear that's why the rubric outlines like linearity, equal spread, all these. And so looking at the conditions, yes, and when you examine the plot, you may see if you are. Yeah, exactly. So the linearity one, if you're examining linearity, the more it looks like this, the better it is. Like this is when we examine the plots. Like a good one will generally look like that, and a worse one will have violations where the line's not going through the middle. So it might look like it's getting thicker or thinner there. That doesn't matter. For the linearity, for this condition, the linearity is only this. And so let's talk about the equal spread condition. And this is the one I'm like least concerned about with this one. The equal spread condition looks good when it... See, we could draw something not linear with equal spread. So just to make it more confusing, this one has equal spread but is not linear. So this is equal spread right now, and the equal spread right here is constant. And the one down here is going to have bad equal spread but be linear. So please be listening in. The reason the top one is good is because of this right here. That's why the top one is good. It's equal spread throughout. The bottom one is bad on the equal spread condition because of this right here. The bottom one is bad because it gets thicker as it goes through, or thinner. It doesn't matter. It just changes in spread. This is equal spread, so we want it to be consistent spread throughout. For the equal spread condition, it doesn't matter if it's linear. That's the linearity condition. So the bottom one is good linear but bad equal spread. The top one is bad linearity but good equal spread. So when I look at mine and I look at the plots, let's go look at the plots again. Where's my check regression? Here we go. So here's the residuals, and let's take a look at them. This one right here is the line. You can see the line. The linearity condition has a problem, especially over here. And I don't really see a change in thickness. I mean, there's just fewer points. Even though we fail the equal spread, I do not see strong differences on thinning or thickening of the model throughout. That would be my answer for this one, is like, even though we fail the equal spread, it's of the least of my concerns because I do not see a strong pattern in the residuals where they get thicker or thinner throughout. So do we fail the equal spread? Yeah, but I'm not that concerned about it. Yeah, that's you could say that. You could say like there's a good linear relationship until you get later in the model. So someone might argue that, and that's exactly the thought you should be giving. Like the graders should give full points. There is no like exact answer. Does that make sense? There's like no real answer to the question. I know it's crazy, but like, there's no real answer to the question. It's just like opinion, but that's a good opinion, and you can really see it right here that the middle of the model has a good linear relationship. Like the line is doing pretty well till you get to the upper portions. Here's the line with polynomial models fit over it. So you can see the polynomials break away at different portions, and then the polynomials really have deviations from the lines at the higher numbers. So your observation is true that for the majority of the weights from about 100 to 250 or so. Exactly, that's all it is. That's perfect, Hale. That's all it is. You're just providing the evidence to support your observation to say, and you wouldn't have to provide this, like you could use the choose order if you want. Choose order is a great way to look at linearity because if you have a good linear model, like I'll do one here. I'll do a good model here in a moment. We'll look at a good model that passes everything. I can make one. Next condition right here. Well, we did the steps. So just to hear the steps fully right here and like see me do the steps one by one. Okay, I look at the equal spread. We fail it. So that's the first step right here. The p-value is bad because it's below 0.05. Next, I look at my sample size. Since my sample size is greater than 25 or greater, my sample size is 699. Since my sample size is 25 or greater, I can continue on to look at the diagnostic plots. The diagnostic plot right here does not really show much of an issue. I want to point something out really big with these plots. So here's a really good question, Kayla, to quiz yourself with. Which of these plots would we look at linearity on? Which of these plots, and I think, don't worry, a lot of people get this one wrong. Which of these plots is the best way to look at linearity? Which you've already looked at linearity. Which of these plots is the best way to look at linearity? Plot 1, plot 2, or plot 3 is the best way to look at linearity. When it comes to linearity, where do we look? Plot 1, plot 2, or plot 3? Where do we look for linearity? That's what everyone usually thinks. That's what you people usually think. But here's a hint. Plot 3 is going to only be for which condition? Don't worry, that's the one everyone thinks it is. Plot 3 is going to be for the what? So when we look at plot 3 is to check what? That's where everyone immediately goes to plot 3 because it's got a line. I got my coffee. So plot 3 is to check the normality of the residuals. So it's to see if the residuals fit a normal curve. So that's a QQ plot for normality. Checking to see if the residuals follow the normal pattern. So plot 3 is normality of residuals. So which one do you think is linearity now? And where is the line? The line is right there. It'll be plot 1. Don't worry. You'll get points today. I'll ask in class. This is, and everyone will be like, plot 3, and I'll be like, no. Having taught this class for 5 or 6 years, I know where people usually go to by default, and I put questions like this on the test, so you were prepared now. So you just get it. You like once you see it, you're like, I got it. I got this. It's like plot 1 is the linearity because that's the line right there. Correct, and that's why I put that space right there because this is also equal spread. We didn't do this to confuse anyone, but the histogram right here of the residuals, it's nice. I don't know. I've actually recoded this at times to remove this plot. It just shouldn't exist. We don't really, yeah. So, yeah. But yeah, so no, and like you would think process of elimination. So I kind of like questions like this, like which plot is the best one to look at. Yeah, sure, Maya, ask away. We'll hop to that next here. Thank you so much, Maya. Ask away about visualization number 6. Put the question in the chat. We'll do it. Charlie, good to see you here. Oh, Charlie, that's so awesome, man. Good to see you. My hair's gotten so long, dude. Charlie, so good to see you. Were you before I started doing it on YouTube or after? Thank you for swinging by, Charlie. I appreciate it, man. I'm like, I remember that name. I think you got like I can't see who's in your figure right there. What is it? Today's Wacky Wednesday. We just gotta hit the button while I drink some coffee. Crash, tell us about Wacky Wednesday. Wacky Wednesdays. It's just crazy. Feel free to swing by anytime, Charlie. We appreciate it, man. I was doing it on YouTube, then you're probably fall 2019, which would be 2 years ago. Like, yeah, I bet you were fall 2019. I'm a Mac. I'm before to what you wrote. You won't color the points because it's quantitative. No need to color points. Oh, I still play Smash. I'm just really bad at Smash on the Switch. I'm just so bad at it. I mean, I'll just flat out say that. I'm bad at Smash on Switch. I'm dealing with it. It causes me pain, but I'm dealing with that realization that I'm not good at Smash on Switch. I'll play Smash on GameCube. Some Smash, that should be Melee, right? It goes Smash, Melee, Brawl, Ultimate, right? Am I correct? It's Melee, then Brawl, right? Can I speedrun? Oh, let's do that. Can you speedrun the answers for 2, number 3? Let's see right here. So which ones are those? Oh, your questions that you posted, right, Kayla? And then the last condition to look at, here we'll do the bad, and then I'll speedrun those, Kayla, and then we'll hop over to Maya's question. The good way, which one do we have left? Normality of residuals. So the good way normality of residuals looks, is when you get your plot right here versus plot right here. And if you have good normality of residuals, this is bad now because I'm on the bad one. Sure, we'll do that color. This is bad, the more it deviates from the center, and this is good. So this is a QQ plot. The straighter it is, the better. So with this right here, this QQ plot looks very like not following the middle line down the center. And let's take a look at ours. Ours also has problems, which is a major concern. Does that make sense, Kayla? How this one has a pretty major concern right here. Like this is concerning, and it's probably due to these points down here. Like these extreme points are located right here. These are the extreme residuals, which I actually see down here in my model. You can see them, where do they just go? These points down here. So these extreme residuals, these very, very negative residuals, which can be seen in the residual plot, like this negative 25 right here or so, is this point right here, which is negative 25 below the line. Like this distance of negative 25 is the distance of this residual right here. And all this plot is the line flat. If you just took this line right here, this black line right here, and made it flat, you would have this residual plot. So it should be a point back here behind that legend, which we can't see. But you're just taking the whole plot. You see this point right here, that one point right there? That one point right there is that one point right there, I believe. If we go down, we should see a point way below, or a cluster of 1, 2, 3, 4, 5, 6 right there. And if you go right here, there's the one point right there, and then you go down, there's the cluster of 6 points right there. Yeah, it's just a line flat. So all you do is you just take this line right here, this black line, and make it flat, and this is the residual plot showing you the numeric quantity of the residuals, which is how far away these points are away from the line. So you're just getting once you see that, it's like, oh, okay, I get what this plot's trying to show me right here. This is the line, this is the distance, and so you can check the linearity because this is the line. That black line right there is this black line right here. That's the black line. So you can see this little bit of curvature at the end right here where the points are going away from it. And you can see it right here where we have a point right there very close to it. And that's that same point right there. That last point is that last point right there. So hopefully connecting the dots, literally, helps make more sense of this. Let me see the other questions you had. And Maya, did we answer your questions fully right there? I kind of speed ran those questions. The p-value of linearity example uses percent. It uses percent. Let me see here. These are great questions, Kayla. Thank you so much. And Tulum, please ask all the questions. Please ask all the questions. The average value y looks as roto nearly independent. applying statistically. Yeah, that's so right here. This one right here, this p-value means we're fine. So this p-value right here means we're fine. So the long and the short of this, even though there's a bend through this, when we do this saturated model, which this is the same idea of what I'm doing right here by saturating the model with too many variables, like a too high polynomial model. So a saturated model is a model with like too many variables in it. Then we're overfitting the models going through each point, and we see that we actually are okay. So this right here means we're okay. Now, it might not look okay, but it's actually good enough. So right now we are good. Does that make sense, Kayla? The big draw away from this right here should be that we are good. Hey, what's up, Colin? Disney's news. I will tell you separately. I just finished. Oh, Disney news. Dude, that's awesome. Congratulations, Colin. So glad to hear that, man. You got to tell me. Message me on Discord or like get a hold of me, man. So let me know the Disney news. Did you see, Colin, real quick on this? Did you see that we're actually publishing a paper? I've been posting about it a lot on LinkedIn. I'm publishing a paper with a guy from MIT, Dr. Andrew Lowe. Just going to give him all the props he deserves. He was one of Time's 2012 People of the Year. I mean, that's insane. Like, you Google Dr. Andrew Lowe, and you're like, oh my gosh. So it's called World of Edcraft. He purposely, he came up with that name. He was like, I have a name for it. World of Edcraft. And I was like, wait, is that like World of Warcraft? And he's like, yes. And I was like, oh my God. I was like, oh, thank you, Colin. No, it's really, I remember Colin came by before he was even in 201, came to my office hours and was talking to 320 students. Should we report it in percent? I do a decimal. If you look at the slides where we do the interpretations, which we'll focus on a lot today, usually right here, yeah, I mean, I don't usually, either way is fine. I guess it does do it in percent. I'd love to see what Dr. I feel like I should call Dr. Petrie. Should we call Dr. Petrie and like get who thinks we should call Dr. Petrie and be like, Dr. Petrie, when you report a p-value, would you report it as a decimal or a percent? So what do you think? He wrote the book on this. You're like, nah, don't call him, don't bug him, don't put him on stream live. Watch him be like, Brian, you always report p-values as percentages. How about that? It's a probability, so I think there's a good argument to report it as a percentage. Does it? Colin says call. Here, wait. Let's see here. We're having special guests. We'll see if. Here, wait. I'll mute myself, and I'll say like I'll tell him I'm muted. So let's have special guest Dr. Petrie. We'll put him on speaker. Okay, wait. I'm gonna mute myself when you call. Here we go. So I'm muting in a second here. I am muted. Okay, I've got Dr. Petrie live on the phone, got him right up to the microphone here. Dr. Petrie, we are talking about the conditions for regression, as you know, linearity, equal spread, and normality of residuals. And we have a really great question right here talking about kind of reporting p-values. And we know that p-values are probabilities. And so we just want to get your input. When reporting p-values to people, especially in the business context, would you report them as a decimal or as a percentage?
Oh, that's a good question. I think people are more comfortable talking about percentages in the business context. So I like saying, there's a 1.5% chance that a random assortment of points would be able to produce a slope at least as big as what you saw in the data. So I like percentages, but you can tune that to who you want to be talking to.
I think that's the biggest thing. And, we just had the business analytics night. And like you said, like tuning it to who you're talking to, maybe sometimes we have to explain things twice or have different ways of explaining it. But no, Dr. Petrie, thank you so much. This is your first guest appearance on our channel. Do you have any other words of advice or wisdom for the 201, 324, 74 students?
Yeah, y'all should become business analytics majors.
I know I love it. If you love it, do it. And Well, thank you so much, Dr. Petrie. A pleasure talking to you, and I'll talk to you again soon.
You bet. Have a good one.
You too. Bye. Now, I think that's a really great answer right there. It really just depends. Until the small, yeah, Kayla, that's yeah. It really just depends. Either way is fine. I do it as a decimal, and I think you could change it. Like some people might understand percentages better. Like what we saw here was blank percent probable. Either way is fine. We'll accept either way. Once again, we look more at the ability to communicate results rather than like rote. It has to be this way. So yeah, great questions right there. And that's Dr. Petrie. Thank you, Dr. Petrie, for I told him, I was like, it's okay. You don't have to appear if you don't want. He's like, I'm good. I'll talk on your channel. I'm cool. Like just calling someone up, be like, hey, you want to talk on YouTube? I really appreciate that. He's very kind with his time and is always helpful towards students. And if I just want to say this, if you like business analytics, do it. If you don't, that's totally fine. I love business analytics. Let me look at your other questions, Kayla, here. Thank you for all the great questions today. Really gives us a whole lot to talk about. I go back and forth for interpretation. Should we use the variable name, like AVG temp, or I'd use average temperature the way you've written it. Yeah. Hey, Aiden. Ah. Oh, dude, that's so crazy. Aiden, so good to see you here, man. That's awesome. It's literally today, Wacky Wednesdays. This is the epitome of Wacky Wednesdays right here. Wacky Wednesdays, man.
Wacky Wednesdays.
This is what we're doing nowadays. We're teaching stats on YouTube, and it's so good to see you, Aiden. Thanks for swinging by. But yeah, anytime you want to swing by, say hey. If you got stats questions, especially, let me know. But I hope you're doing well. Trying to remember like what year you were and everything. I'm like, man, so much time has passed, right? Let's see here. So, Kayla, to specifically answer your question, what we have is, I would probably use the best context. Like, although you can write AVG temp and we'll give full credit, it's probably better to write average temperature. Does that make sense, Kayla? I probably wouldn't write AVG temp. Like, if I'm writing this in a business report, I'd probably write average temperature. But, you know, for our class, we can write average temp. We're not like, we care more about like, we're not going to go like so small, minute details. But if someone uses like 201 interpretation for the slope, then we're gonna be like, that's not a good interpretation right there. Like that doesn't like convey the correct knowledge or convey the correct idea of our model being an attempt to make predictions. It makes the 201 interpretation of the slope makes it sound too much like it's cause and effect. So that's so funny. The YouTube algorithm suggested it. That's so crazy. Confused by the wording on slide 44. Let's look at slide 44. Yeah, exactly. Well, you're doing a great job. These are the great questions. So confused about the, let me see which part right here. Confused by the wording. Okay, look. Oh, let's look right here. I wasn't like, look. Consider the relationship between the area. I'm going to disappear. We'll go over to lecture slides. There we go. Consider the wording. Consider the relationship between the area of a house and its selling price. The relationship looks linear, but the vertical spread increases for larger areas. Okay. So we're looking at a model right here. Let's draw through it. And let's just talk about what we're talking about. The relationship looks linear. So what they're talking about right here is they're talking about this. So it looks linear. And the vertical spread is this right here, which is the strength of the model, which indicates a weakening of the strength. Plotting the squared residuals. So this is our residuals right here. So the plotting of the squared residuals. So plotting this, come back. Squared residuals right here versus our reveals and association. Plotting the squared residuals versus, oh, that might be a typo right there. Versus ours. That might be our values. I think there is a typo. Reveals and association. Yeah, right here that we know. Is that the, oh, sorry, squared residuals. Oh my gosh, my brain is not working today. Brain's not working. Brian's brain's not working. Versus area. Okay, wait, area right here. Okay, because areas, there we go. That is a typo. I need to correct that. So there's a typo right there. That should be area. And that's the X value right here. We don't always look at the squared residuals. So the reason, I just noticed that too. The reason we would square the residuals is all the residuals would be positive then. And it looks to be that there is some sort of unexplained variation. The p-value of this test is this, implying that the spread can be predicted by X. We conclude that the vertical spread is not constant. So this is basically the fine details of how it's calculated. And don't worry, you won't have to know this. And so here's a really good important thing. You ready for this, Kayla? Here's a really good important thing. And this is the exact details, which is excellent, excellent, excellent. So when you look at this right here, the big thing we should notice here, let's highlight everything that we're looking at. So I thought, oh, wait, remember, that is correct. We do want a p-value above 0.05. That is correct. And so when you look at this right here, so that p-value is super low, right? Because it's 2 to the 10 to the negative something crazy. That p-value is super low, which means you do what for the null right here? This p-value here is super low. Yeah, exactly. It's not constant. Exactly. It's not constant. So when you look at this right here, this p-value is super low, which means we reject the null. And the null for the linearity one, which we might still have up, we drew out what it should look like. Not this right here, but where's our drawing? No, we're looking at equal spread right now. So let's see if we can get back to equal spread. Our equal spread drawings. There we go. We're about to see it again. Hey, there we go. So here's the equal spread drawings. And you can see right here that we have some sort of equal spread problem for the low p-value. So this is a p-value less than or greater than or equal to 0.05. Greater than or equal to 0.05. And a p-value less than 0.05. So, yep, exactly. Yeah, if you reverse it, you're like, wait a minute, what's going on? It's reversed. Why is it... You're just like, it's not making sense. I thought it was this way, but it's not this way. So exactly, and hopefully, let me see right here. So great questions, amazing. Transform models look worse, even though the R squared is higher for the transform model. Oh yeah, that can happen. Transform models can look worse. So what's really cool about this function Dr. Petrie created, and great work, like this puts you through the assignment right here. Dr. Petrie, let's take a look at the function because it's so cool the way it works. If you look at the fine transformation function, like we're gonna go just take a look at it. So let's clear this out. And here is, no, we got to delete this off. So let's look at the fine transformation function. And here's the fine transformation function. So this is the function Dr. Petrie created. And the way it works is it's going to go through a vector of numbers and calculate the R squared. So it's going to go through a vector from, by default, -3 to 3. It's going to go by increments of 0.25. And then it's going to look at it's going to report back all R squareds within 0.02 of the best R squared. And so it basically just goes through and starts making all of these models right here where it raises the X and Y to these powers. So it's like, it's going to use tons of for loops right here. If you look at it, it's a nested for loop. So it's going to go through and like raise Y to -3 and then do X to all the -3 to +3 values by whatever increment, 0.25 by default, increment those through, then move the Y over to -0.275, and then increment the X through. So this is the for loop going through, moves Y over, increments X through, and it's making all of these models here. And we can see all this output very quickly by just going over here to the fine transformations code and just putting our model in. So remember, this is an iterative process. It would help if I spelled it correctly. This is an iterative process right here. It's mad about the graphics. This isn't really. It's an iterative process that goes through and looks at all these models. And we see here what the node transformation model looks like, which is our model. And you've got this humongous outlier over here. Here's the node transformation model. We got outliers. We've got the linearity problem. We've got outliers down here. Equal spread, small problem, but we were like, I don't know. Equal spread was least of our concerns. And then over here, we see probably better linearity, a little bit of a problem over here. This is the highest R squared, huge outlier. Like that's whatever point that was in the original model, we are taking and raising to -0.5 there. We're highest rated to 3. So height raised to 3. So that's raised to the third power. Yeah. So, I mean, that point right there is ridiculous. That's insane. So with the transform model, we increased the R squared from 0.361 to 0.41. And what's really cool about this code, like what I really love about this code is you should be able to go here. Is it from, what is the syntax of it again? The syntax is, yeah, it's sequence. Come on. Show me a sequence. There it is. Powers equals, and then it's a sequence. Okay, good. And then threshold. Okay, so let's go model. Powers equals sequence from -5. No, I do want that one, don't I? Yeah. From -5 to 5 by 0.1. Yes. Ha 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 ha. So this is even crazier now. Let's clear the output and run it again. I'm overfitting the model. Dr. Peacher's probably watching right now. I just wanted to see how high of an R squared we could get. But I don't know why it's reporting. Oh, probably because I've got my decimals weird right now. I've got my SciPen. Sorry, Dr. Petrie. He's totally watching right now, and he's like, Brian, what'd you do to your SciPen? I change it so often, I don't know what it's supposed to be done by default anymore. Okay, there we go. So stop reporting crazy. Oh yeah, it wants to report crazy decimals. I'll let it do its thing. I'll let it do its thing. So here is all of the output right here. Does this make sense what this is doing, Kayla? Like, do you understand algorithmically what this is doing? It's like it's raising y to the -5 and then changing x through all the powers and looking at all the models it's creating. It's calculating all the R squareds for everything. And then it moves y over to -4.9 and then runs all the x's. And then it moves y over to -4.8 and then runs all the x's. Yep. So it's a nested for loop that changes the x and the y value. And then we can control what it's doing via this right here. We don't have to do this, so we can just use the default. And we can fine tune it. But now the graphics will show you the best model over here. So up here is the highest R squared. And then we see the second highest R squared. And we see the third. And the reason you'd get all four of these plots is because there's really oftentimes very few differences. So maybe you'd look at one that is the best. So now let's go ahead and create our model. So we see that we need to raise height to the third. So I'm going to go right here and go survey 11, 10, and go to height. And we're going to raise this to the third power. And let's call this transformed height. And then we're going to go here to weight. And so, really? And then we're going to go to weight. And what power for my best model do I want to bring weight to? So what power for my best model do I want to bring weight to? For the best model, looking at the best model right here, what power should I bring weight to for the best model? And these will be vectors saved to the global environment. Look at that height. It's height to the third power. So for my best model, I want to raise weight to the what power? Then we can take a look at this model. It's kind of a ridiculous outlier. That is, it's not good. That is going to hurt the normality. Exactly. -0.5 obtained from right here. Also obtained from the output. You can look at the x power right here and get the y and x powers. Same powers as right here. 3, 3, 0.5, -0.5, -0.5. So make sure, be very careful. I've seen people do this. That will cause a problem. That's raising to the -1 and then dividing up by 2. Be very careful. It needs to look like that. Or it could look, you wouldn't need the parentheses now, but it could look like this. That'll obtain the same result. Let's call here transformed model. And will that? Nope, still won't. Darn it. I don't know. I just want that space now. They've won me over to the underscore team. And let's go here to transformed height being predicted by transformed weight. And there we go. There's our transformed model. Let's visualize it. We're going to see this here with the high outlier at the end. So get ready to see that in the transformed model. And there's our ridiculous outlier at the end. Overall, equal spread looks to be way better. So when I'm looking at this right here, I'm thinking, I think equal spread is going to have a way higher p-value. If I am to guess, just looking at it visually, linearity might be more improved. Equal spread might be better. I think we're going to at least see the p-values on those. We didn't, and then the normality, we got issues on normality down here with these low ones. That's not insane, but that's really bad. This is bad, super bad, insanely bad, super bad, kind of bad, super bad, bad and about what we'd expect bad. So I think the normality of the residuals is going to be a huge problem here. That's where our biggest problem is going to be if I am to look at that. And let's take a look. And the answer is normality. Look at that normality. Whew. Oh, tell me about that, Kayla. So what happened there? I did get the one thing. It was the first thing I thought that was better. What does that mean? We've done it. We passed one condition. One condition. That's the answer to it. One condition was passed. I put test questions like this, and I also want to explain one thing after this. But does this make sense where I'm like, oh, we actually pass it? I mean, just barely. But my visual inspection of it, too, didn't really turn up much of a problem. So I sent you mine. The transformers look worse, and all my POs drop. Only normality was below. So yeah, you might actually get worse. Yeah, so you can actually have worse assumptions. So let me ask you this. You ready? Would you rather... So here's the question. Ooh, this is a good question. Let's say this. Here's the choices. Model 1 just barely fails all the assumptions with p-values of 0.049 with 2,000 data points. It has an R² of this. Model 2. I should just put this on the test. Like, I flat out just want to put this question on the test. Model 2 passes all the assumptions with p-values of 0.98. See, people might think I could just see, I don't want to put those people might think, oh, it's statistically significant. Just barely fails all the assumptions. There we go. Passes all the assumptions and has an R² of 0.02. Which model would you use and why? Which model would you pick, Kayla? So model 1 just barely fails all the assumptions with 2,000 data points. Passes all the assumptions with, let's go here, 40 data points. There we go. I'll explain kind of a concept behind this too, because it relates to statistical power. So, and it also relates to all models are wrong, because enough statistical power and you'll find out your model's wrong, because all models are wrong. Model 1's this is like, I don't think you can argue for model 2. I'd love it if Dr. Petrie, if he saw this, he'd be like, yeah, model 1, you're going to probably fail assumptions. We didn't fail them badly. It's like, yeah, there's issues, but our model is a very good model that explains 98% of the variation. There's small problems with the assumptions. This model right here, model, and let's just do this. Model. Now this is like a double. I'm also, I don't want to tell you the p-value of the model. I mean, I could. There's lots of ways I can phrase this question, but I just said this model is not statistically significant right here. I just said that this R² in this model, by saying the model works the same as the naive model, I'm saying it's not statistically significant. So understanding, the naive model is the model that is the mean of y for quantitative models and does not explain any variation more than the mean of y. Then if our model works the same as the naive model, our model is just as good as random chance, and it doesn't do any reduction to the sums of squared errors. So this model here, right, is you just wouldn't use it. It's as good as the naive, so your model would be bad. So an important thing to know, though, is when you have a very large sample size, the larger the sample size, the higher the statistical power. And we cover that at the end of 201. So larger sample size means more statistical power. And statistical power is the ability to reject the false null, or I like to call it the ability to find results when results exist. Because if the null is false, then results exist. And if we can reject the null, then that's the ability to find results. So the ability to find results when results exist. It's like to say, let's say speedruns really help my students. When would it be easier to find out speedruns help my students? If I get data from 40 students or 2,000 students, when would it be easier to find out and have evidence, reject the null that speedruns don't help, because that'd be the null. The null would be there's no difference between students who use speedruns and don't. When would it be easier, with 40 students data or 2,000 students data? So when would it be easier to reject the null, when I collect data from 40 students or 2,000? And that's what statistical power is. Like, if there is a difference between students, then the statistical power, the larger sample, exactly, because larger sample size, and there's more that goes in statistical power, but one big concept for it is the larger the sample size, the higher statistical power. The other two concepts are the alpha level and the effect size. I'm not going to go to a whole lesson on right now, though. But with that, exactly, Kirsten, I love it. Let's throw some 50 points again. Thank you, Kirsten, everyone. And this is 201 concepts. So if anyone 201's listening in, we do cover power at the end. And it is an important topic. So I want us to think about this. If our model, how many models are wrong? Like, how many models are wrong? And this is a big concept, and it really helps with understanding why we look at the plots. So this goes back right to here. Like, we're looping back to this output. How many models are wrong? How many models are wrong? Because we're going to be talking about this right here. How many models are wrong? All models. So if we get a large enough sample size, what are our p-values probably going to be? Like, with a large enough sample size, our p-values are probably going to go towards 0. Like, if you get a big enough sample size, you're probably going to fail all assumptions. Like, if you get 10,000 points, your model's probably going to be like, nope, bad model. So then we don't just say it's game over. If we have a very large sample size, we acknowledge that we're probably going to fail these assumptions. And what do we do? Because that's the second step. What do we do since we say, we're probably going to fail the assumptions if we have a large sample size? And large is, like, you'd be shocked because a lot of times you can only get 10 or 12 data points. Talk to VetMed. They don't get a lot of dogs, cats, ferrets. They don't, sometimes they're like, we have 10 dogs to do research on. And it's like, that's a good sample size. So if we get a decent enough sample size, what do we end up doing if we have a large enough sample size? Because we know we're probably just going to fail assumptions because all models are wrong. Since we know all models are wrong, we then ask, how bad did we fail? This part down here is the how bad did we fail the assumptions? So we have to look at the plots and make some assessments ourselves to be like, we did fail the assumptions, but how badly did we fail them? So, maybe the linearity looks something like this. Like, let's say the linearity, which we failed on, let's say, looks something like this. And we see over here at the end, maybe the true model would go something like this right here. I have no idea what that pen even does. So we see maybe the true model would go like this. So would you use this model or not use this model? Would you use this model or not use this model? So you just failed, and then you look at it and you go, well, I failed the linearity, but that's what my model looks like. You're welcome. Head to class. Don't worry. I would use this model. Great questions today, Kayla. I hope this helped a lot. Really good talk for 320. This is I'm going to try to put parts in this for 320. Amazing work. I hope this helped with understanding the conditions. This is what we're covering in class. So you'll be like, when you hear it the second time, you get to test, you'll be like, boom, I know the answers. So yes, I would use this model right here. I'd say it's good. I would say it's good. Are there more questions? Who has more questions? Really good talk for 320. And we did the transformed models also. So we pretty much did all of 320's assignment today and talked through checking the regression, talked through the transformed models. Excellent, excellent work. Let's see right here. Called Dr. Petrie today. Dr. Petrie's advice. Kirsten, anybody, if you have questions, let us know. I've got one sip of coffee left. Coffee's over. We had Colin drop by. We had people who live next to me drop by. It's completely wacky Wednesdays. This is a really, really fun, interesting office hours today. If there are no other questions, could we look at this? Yeah. Kirsten, I'm throwing 50 points. I don't care. Kirsten, that's such an awesome question. I'm very interested in the survey too and we'll look at it during let's go look at it. No, that's 100%. Let's go look at it. Once again, this is the data collected on 201 students, asking them. I had to reset the data. So are you in today's class, Kirsten? I'll send out a reminder if you haven't done it. I'll send it out in the chat for people who haven't done it to do it. We can look at here. We could do. Here's a different type of model. You ready? Ooh, here's some fun things Jump can do. Let's go here to analyze. Let's go to fit model. That's what I'm looking for. Good thing I've learned how to use Jump. I used Jump for 5 or 6 years consistently, and then I've been using R more consistently. Okay. Check this out. This is the fit model platform. It allows us to do a multiple model. So instead of including, previously we did what would be called the bivariate analysis, and now we're going to do a multivariate analysis. Does this make sense that these are all bivariate displays? We have basically side-by-side box plots. It's not showing side-by-side box plots, but I can make it if we want. Now that's side-by-side box plots. So it doesn't show box plots there anymore? Oh, it's a side-by-side. If we put box plots over it, I thought for sure. Oh, you have to go to quantiles. There we go. There's side-by-side box plots. And then, so we're doing bivariate displays of side-by-side box plots, bivariate displays of scatter plots. So these are all bivariate displays. So instead of going bivariate, let's go multivariate. So now we're doing a multivariate analysis here, and we're going to make a model to figure out someone's success. This is pretty cool what Jump can do right here. So here we go. Oh, no. We gotta, wait, that's an overfit model. What's our R squared though? The model is statistically significant. The residuals actually don't look that bad. We don't have a lot of statistical significance. Sorry, I overfit the model. Statisticians are screaming at me right now, and they're saying overfit, and yeah, lack of fit. Yeah, this is yeah, there's a problem. Does it not show the R squared? Where's my R squared at? I just want to see R squared before I throw away this model. Really? Jump, where do you put the output? Where's R squared? Oh, wait, there's the R squared. Only 36%. That's kind of a bummer. Okay, we're going to do this the right way now. That is an overfit model, and it even told us it was overfit. We're going to go here to a stepwise model, which we do cover in 320. We do cover stepwise models. Let's go here to run, and I'll explain what a stepwise model is. So what this is going to do, and I can probably tell you the variable it's going to select first, is it's going to look through all these variables that we've collected, and it's going to find the variable that is most significant. So when I go here and go to step, it says the variable is what was your Canvas content grades. That is now in the model, and we've explained 12% of the variation. The next variable it chooses is do you attend the SI reviews? And we're just going to hit go right here, and it's making a model. So this model now explains 30% of the variation in your test scores. Does that make sense, Kirsten, right here? This model has an R squared of 29.18, 30%. You're like, Brian, that's not 30%. I'm like, almost 30%. So this model has an R squared of 30%, and it would typically miss predicting someone's test score by about 9 points, which is a large typical miss. I wish we could do better. We just have to get more data, ask more questions, and figure out what questions to ask that explains the variation and why people are acing the test. So our model has a slightly large typical miss. Like, I like this model, but I want us to do better. Yeah, exactly. It's less pictures, kind of like a decision tree, because a decision tree is a multivariate analysis with multiple X's, and this is called stepwise regression. So we're actually doing a regression like we do in the regression class. They'll be doing this soon. I can go to make model, and let's go ahead and run this model. And what's really cool about this is we can go down here, and does it not have that? I saw it a second ago on the other one. Here it is. Yes. We can go here, and we can do predictions for individuals, and we can predict what someone would get. So we can predict if you did your Canvas content quizzes. So here's the different levels here. Is it treating that one? So always, if you attend SI, do you watch office hours? I think it's the people who watch the recorded office hours. Do you take notes? So our model, if we go through here, and I could save the predicted on individuals, you can see what people would be predicted to make. And probably even better than this, we're going to go here, and everything is statistically significant in this model. So everything accounts for, with the other variables in the model, accounts for variation in the model, like, going to SI, your grades on Pearson. All of this came out statistically significant right here. Explains 30% of the variation. Residuals look kind of interesting. A little bit of heteroscedasticity there. Let's go here to the save residuals. Oh, no. We don't do save residuals. Okay, cool. So we're saving the predicted value. So what we're going to look at is we're going to go over here and look at what people were predicted to make. We're going to sort this column right here by ascending. I think we want to do descending. So here is using my formula. And let's go to sort. Ooh, that person had a very small residual. Here's what these people were predicted to make. Here is the person who was predicted to make the highest test grade, and they had a residual of 9 points. So I want you to think about this, or -9. They were predicted to make a 95. I can tell you what they actually made from the residual. And look, not many of these residuals are too large. This person has the biggest residual right here. They have a residual of -18. So they're a lot lower than they were predicted to be. But this person has a residual of -9. They should have an 86. So if you go over to their actual grade, there they are with an 86. Does it make sense what I'm looking at right here? My predictions using my model. And you can see this person made an 86. They were predicted to make a 95. They had a residual of negative 9.15. And these people were predicted to make the highest grades. So this person who was predicted to make the highest grade on the exam, does that not increase the font size? There we go. Oh, it's going to do it. They watch Kahoots live. They do their Canvas content. They don't go to SI. They watch recorded office hours. They take notes always during class. They're very attentive. How often do you chat during class? They chat often. My Pearson grades are high. They complete all the visuals. They studied 2 hours for the test. They're in the Tuesday, Thursday section. They did not use speed runs, which is all right. And they started studying within 24 hours before the test, which was not part of our model. Here is somebody who did very well on the exam. These people did very well, and they were predicted to do well. This person right here watches the Kahoots live. They have an A here. They do not go to SI. They watch office hours live. They always take notes during class. They're always attentive. How often do you chat during class? Sometimes. And my Pearson grades are an A. They completed all the visualizations. They only studied one. It's so crazy. You know what's interesting? In this model, I want to point something out. What do you notice is not included in this model, Kirsten? In this model, do you see how much people studied for the test? So in this model, do you see any variable for how much did you study for the test? Which is crazy to think about is not significant. Which we're finding out it's not what you do to prepare. Like, it's not how much you study for the test. It's what you do before the test that matters. Like, if I can stress one thing, it's not studying for the test. I mean, studying matters, of course. But the thing that makes the difference, I know that's weird, isn't it? It's not like studying makes people do better. It's what you're doing beforehand. And I really think it's because you have to hear things 2 or 3 times. And this is the real data. And you can look at what's like most statistically significant. Canvas content explains what the other variables are. It's up there. We also see like, do you take notes is super significant. And then also we see how are your My Pearson grades. So this model accounts for 30% of the variation. That's pretty awesome. We're going one higher though. We're not done. But wait, there's more. There's always more with statistics. Let's go here and go to redo, relaunch analysis. And now we're going to go here and do I'm trying to think, we're doing an interaction model. So this will account for interactions between the variables, like maybe someone who takes notes during class, but studies more. I guess I could do all of them. You know what? Why not? If we're going to go crazy, we're going to go crazy. Let me remove this out because it's already done some more decent analysis. Let's go here. Let's restart the analysis. And let's put the Y variable here. Let's go grab all of these. And we don't want the residual columns though. So that would, yeah, we'll get great predictions if we use predictions to make predictions. So let's go here to cross, and then we're gonna go even one crazier than this. But wait, there's more after this. So here, let's cross these. Wait, that's not what I wanted. Let's go here. You're like, Brian, you gotta stop, man. I need to go to macros, I think. Macros, factor to degree. Sure. Awesome. Cool. Okay, we don't want to include all of them. Let's go stepwise. Here we go. Let's make the model. And the answer is, now we've explained 46% of the variation. So this is our best model right now, including interactions. So we've explained 46% of the variation. Let's go ahead and make this model. Here's the model, way more variables, way more interactions. And here's the model right here. You do notice that there are rather large residuals. The model gets tighter near the top, so there is some heteroscedasticity issues, predictive strength. Lack of fit turns out good, so our model might be a good model. Wish it did more tests than that. Residuals are looking all right. It's pretty bad. I think that's 3 standard errors. The residuals, so yeah, they're standardized, so that's a z-score of -4. So when it says standardized right here, these are all z-scores. So that's a mild outlier, and these are extreme. I wish it did 3, but overall we see some problems here on the low side, which are going to be these points down here. There they are right there. So issues. But overall, and it looks like we only have a few variables with the interactions. We're going to go one crazier on this, though. And there are things that are not significant. You might say, well, Brian, your model has things that are not significant now. But in the multiple world, things that are not significant might help the overall model. And that's the weird thing about the multiple model here. Let's go ahead and save the predictions right here and find out who from this model that does better was found to do the best. So we're going to go here to So we have columns. We're just saving the predicted values from this model. Does it make, Kirsten, tell me, because hopefully I'm not talking too much and too quickly. What I'm doing right here is I'm saving people's predicted scores from my model. So I'm using that model to make predictions, and then I'm looking at the people who were predicted to get the highest scores. This was my first model. This is my second model, and I'm going to use this. I'm going to sort it by the descending. Wait, so how does Jump know how to choose will raise their predicted scores? So it does a stepwise model, basically tries to, oh gosh. I'm going to try to explain it without getting too complicated. Here's what Jump does. I give it all these variables. So what Jump does, I'll like explain it without, let's do a simpler version. So I'm going to give it all these variables right here. Does this make sense? I'm going to give it all these variables. And when I do a stepwise model, Jump's going to look at all of these variables and say what variable helps the most from all of these variables. So when I hit step, it basically walks a variable into the model. It's like, what is the best variable? And it found, oh, you see, we left the residual in there. Let's lock this so it can't put that in because we didn't, that was by accident. So when we let it look through all the variables and it says this was the best variable. And then we hit step again and it says this is the best variable. Now you could keep hitting step, 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 and it's basically walking more variables into the model, or you can hit go and it'll just like go through the process of stepping things through. Now Jump has ways of knowing when it should stop. It looks at different things like the Akaike's information criteria or the Bayesian information criteria, I think, or the Fisher's information criteria. There's tons of ways to tell it to stop. But with talking about, these are called how close our model is to the truth, if any statistician is watching, with those criteria right there, it can make up a choice when to stop. So Jump is using kind of metrics we've calculated in statistics with those AIC and BIC over there to figure out when to stop putting variables into the model. Does that make more sense, Kirsten, I hope? Like Jump's using, it's putting variables in and looking through all the variables and saying, add this variable, add this variable, add this variable. And then with kind of advanced statistical algorithms or advanced statistical formulas, it's saying, yeah. So it's basically making choices for us and doing all of this. So what I did a moment ago is I made an even bigger model with more things and let it pick from more things. And we'll go here to sort descending. And it's going to sort it. And now let's look at the people who are, look at this. Look at all these people right here. The top, we'll just go top 10. The top 10 people, 98, 88, 94, 88, 98, 93, 86, 88, 88, 88. The top 25 people. The top 25 people in our model. I'm trying to zoom out one time. The top 25 people in our model. Wow, the lowest grade was a 73. The top 25 people from our model. One person made a 73. One person made a C. The top 25 predicted from our model. This person in the 100 was not the top predicted. So let's look at what these people were predicted to make. 97. This person was predicted to make a 97. They didn't make a 97. They made an 88. So they watch Kahoots live. They have a Canvas content average of an A. They don't go to SI. They watch office hours recorded sometimes. They might be watching now recorded. Hello, this is you. Do you take notes while watching class? Always. Are you very attentive? They are. How often do you chat during class? Often. They have great grades in my Pearson. They stayed 3 hours to the test, which was not part of our model. And Tuesday, Thursday, all of this right here. So that is the formula for the person who is predicted to make the highest grade. So this is your model right here, which explains over 50% of the variation and why people did well on the test. About 50% of the variation, or 50.2, I think, from this model, which is more variation we understand and why people are doing well. This is the person who did well, and this is what they were predicted to do well. They made an 88, but they were predicted to make a 97. You can see other people right here did really well too. Like this person right here made a 98, and the formula they followed is, do you watch Kahoots? They watch them recorded. They have an A there. They watch recorded office hours. They always take notes during class, and they're always very attentive. These two things I think are not showing up by chance. Let's look at the people who were predicted to make the worst grades. Sorry. The people who were predicted to make the worst grades, and look at this. Look at the bottom of this. Down here at the bottom, what do you notice? We only see an 86, which is a good, and there's an 87. There's 2 Bs, and that's it. So down here at the bottom, you've got 2 Bs, and up at the top, you've got like 1 C. So lots of C's, lots of D's, some F's right here. This person was predicted to make the worst grade, and they might go against, so do you watch Kahoots? Never. Do you go to Canvas content? They got to be there. They go to SI, they watch Office Hours Live. Don't worry if this is you. Remember, some big things we're going to see right here. They're mostly attentive. So we saw that being more attentive during class helps out. Do you take notes? Taking more notes. But I really think Canvas content's going to be big. If this is you, I think Canvas content's going to be a big help. And also taking notes during class and being more attentive during class is going to help out. My Pearson grades also. I think those are the things we saw. So here's my suggestions if this is you. Canvas content, number one. We've seen that that's highly connected to it because they're on the test. Check out the Kahoots. We saw that is connected. That was part of this model. More attentive and take more notes. So we got this. We got this right here. Let's go one crazier. So Kirsten, are you still here? I hope. Because here's where things just go insane. Because decision trees is not where it ends. We're going to do boosted models. We're not doing decision trees. We're going to go up to boosted models now. So we're going to go to partition. And we are going to predict somebody's score using all this. And we're going to go to the boosted trees. I think we want to go to boosted trees. Yeah. Cool. We won't do a validation. Sorry, Dr. Peach, we're not going to do validation. Too much. Kirsten, that's awesome. We can do bootstrap trees too and boosted trees. Okay. So let's see what happens here. Okay, number of layers. I haven't done this in a while on Jump's platform. Learning rate, that is the shrinkage. And max splits per tree, suppress multi-thread. Okay, cool. Yeah. It doesn't let you choose a vector right here? That's so boring. Wow. Wow. Kirsten, why did I just say wow? Like there's something on this screen here that just made me go, wow. Like instantaneously. It was just boom. My head just exploded by this. We gotta hit the button. I just saw it immediately. My statistical eyes were immediately drawn to this. Like within seconds. Within milliseconds, my eyes saw this and I was like, holy mackerel. And I'll be showing this during class. Kirsten, I don't care. 100 points right there. Which means this model right here, this model I've made does what? Just think about how we talk about R squared. This model now accounts for 72.4% of the variation in people's grades. And it typically misses for 320. The model typically misses predicting someone's grades, like on average misses by about 5.5 points. So if I say you're going to make a 90, probably make between an 85 and a 95. So if this model, it typically misses the prediction someone is going to get on the test by about 5-ish points. So you know what we're going to do? We're going to save the predicteds again and look at those people who are the best and the worst. So let's go here. This is why I find this fun. To me, is just fascinating. Fascinating. It's just so much fun. And you see there's difference in the predictions of the models. So let's go here. Ooh, you see maybe these people weren't predicted to be the highest now. This model does do way better. And there we go. Okay. The person who was predicted to make the highest right here, they made a 94. So now our model's doing even better because this person was predicted to make a 96 via the newest model, and they made a 94. They go to Kahoots Live. They they get A's on their Canvas content. They do not go to SI. They watch Office Hours Recorded sometimes. Hello. They sometimes take notes during class, but they are very attentive. How often do you chat during class? They're often chatting. They're chatting a lot during class, it seems. They have A's on my Pearson. They do all the visualizations. They studied 3 hours. They use some speed runs right here. So this is your formula right here for success. This person right here, they were predicted to do well, and they did do well. 94, great job. If this is what you did, you had the optimum formula for success according to the tree. Down here at the end, we'll look at 2 people here. So do you watch the Kahoots? They're watching the Kahoots recorded. What is your Canvas content average? A B. They do not go to SI. So we see, once again, I think SI is great. And they watch recorded office hours. Do you take notes during class? Sometimes. They're mostly attentive. Do you chat? They chat sometimes. And I really think the variation right here, they use none of the speed runs. Within 24 hours, they were studying before the test. But I think right here, we're really seeing the Canvas content's a huge thing. So this right here is the formula we're seeing for, not success. And we'll look at the other person too. Thank you everyone for all this data. This person right here never watches Kahoots. I think that right there is a big thing. Like I think the Kahoots, so they're very distracted during class, and do you take notes? I think this is a big thing. I mean, just look at this. I can tell you, we haven't looked at the second person right here, and I'll bet you good money that they're very attentive and they're taking notes during class. So this person will be a different formula than the person up top. I'm looking at the third because it looks like these two have the same predictions, so the tree did them the same. They are very attentive, they chat during class, and they take notes. I'm not shocked by that. How does boosted trees work? Oh my god. That's such a good question. Okay, so I might pull up the notes on it. Boosted trees are trees that learn from trees. Kirsten, since you asked, I'm going to show the notes, and I'm just going to show this fourth person right here because I would not be shocked if this fourth person is very attentive and takes notes during class. Watch for it. You ready? Very attentive. And do you take notes while watching class? Always. Not shocked. Not shocked. They don't watch the Kahoots, but I was not shocked at this right here and these. Like, I'm not shocked by these formulas right here. And they started studying 24 hours before the test. They studied 1 hour for the test, and they made a 94. They started studying 24 hours before the test, studied 1 hour. There you go. It's all about the prep. That's what we're learning right here. It's all about what you do before the test, not the night before the test. So because this person, 24 hours before the test, 1 hour study, and they made a 94, and they were predicted to make a 95. Boosted trees. Let me pull up the notes on it, and I'll tell you a little bit about boosted trees. Thank you so much, Kirsten, for all the amazing questions today. If you can't tell, I love this kind of stuff. And I was saying to a 1 especially, or I was saying to 320, you have to have an understanding at least a little bit on what these algorithms are doing. So you have to know a little bit about what's going on right here. What? 2 seconds. I'm trying to pull up the notes right here. I went to my class and it wouldn't let me see the notes. I'm like, how dare you? I have the notes. All right, here we go. Well, let's pull up the notes on boosted trees because it'll help to see it. Tree models. Here we go. And Kirsten, if you want, I can send you this. If you want to read more about tree-based models, let me put, I'm going to go to space real quick. What is your major, Kirsten? Are you business analytics? It doesn't matter if you're not business analytics. That's totally fine. It's even actually more amazing if you're not business analytics. You just have an appreciation for this. Just wondering, like, what are you majoring in? Like, if you're not business analytics, I think that's even more awesome. But I don't know. So if you are business, that's like awesome because that's, the big questions. Here, I'll go over back to boosted trees now. All right. So there's boosted trees right here. Let's go over to boosting, and this is what boosting is all about. Your statistics, yeah, great deal. Like, I'm not shocked because you're like, so tell me more of this. So when we talk about the interaction depth right here, like all this goes into really great detail on it. Wait, where are the pictures on this? Where are the pictures? Where are the pictures on this? Really? Interaction depth is how many times we split the tree. I don't know why. Did we make consolidated notes of this and we took out? So the interaction depth is how many splits we do in the tree. So this tree has an interaction depth of 1 right here. This tree has an interaction depth of 2. This tree has an interaction depth of 3. So what happens is when we do boosted trees, like, it's a lot less fun than Stats 1 notes. I'm sorry, Dr. Petrie. When we talk about boosted trees right here, in a boosted tree, it's going to basically have this lambda, which is going to be the shrinkage, which is the amount of information we're kind of carrying over between trees, or the learning rate, basically. And we're going to continue just learning from each tree, and it actually does these sorts of formulas for us. And I can send this to you if you want. So you can see right here, the lambda we set. We can have like a slow learning tree or a fast learning tree. And yeah, so it's the shrinkage or the learning rate the tree does. And then we're going to choose like how far we have. So we actually use a tuning grid for this. And so if I go over and start doing it in R, yeah, hey, if you want to ever know more about business analytics, let me know. Yeah, whatever. If you're interested in these things, I'm more than happy to talk about it. Here's the parameters, the number of trees, the interaction depth, which is basically how big we grow the trees. And this is number of minimum observations in a node, which is when we get to a node, which is the bottom of the tree, how many observations do we allow for the minimum? And this is a lot of the parameters Jump was letting me control for. So we're talking about this right here. This is the min observations per node down here, but this is just a tree right here. So a lot of really cool topics in this. I'm going to head off here in a second. But if I can, we got up to 72% of the variation. Now I should be using cross-validation and holdouts. I know, Dr. Petrie, I know. Well, we should continue through, but I'll be showing this in class today. And wow, that is, come to class, take notes, be attentive, and then you get to study 1 hour for the test. That's what those people were doing there. We can't say it will work for everybody, but it did work for those people. We'll put on a little music here and we'll end the boosted tree. I knew boosted trees would be the best, so I saved it for last. Yeah. Email me and be like, Brian, send me those notes. I'll send you those notes. And maybe I'll code it in R, and I'll see if I can get better results in R, because I can run more algorithms in R. I can use tuning grids, which is what you should be doing. That's a whole nother talk about the tuning grid, which is things we cover, like why do we use a tuning grid? Why do we use holdout? Why do we use cross validation? So there's a lot more to do that I was kind of like background knowledge I know. And so some statistician's going to walk in, Petrie might be watching, he's like, Brian, you did not cross validate your results. How do you know that it works on new data? And I'd say, I don't. I will cross validate later. I will have internal and external validation of my model. Statistics is a lot of interesting stuff. You're welcome so much, Kirsten. Well, what am I teaching next? Teaching BES 320. With that, everybody, bye for now. Bye. Awesome stuff today.